Hi, everyone. Welcome to the in-person audience. Welcome to the online audience as well, to this seminar organized by the Institute for Experiential AI, EAI. So as you know, we host seminars every 2 weeks, and we combine the expeditions and the distinguished speaker seminars. So during the next hour, we're going to have a presentation of about 40-45 minutes, and then there will be time for question answering. So please feel free to ask questions in person, and also the online audience, you can ask questions remotely anytime during the talk. It's a big pleasure for me today to introduce our speaker, Walid Saba. Walid is a senior research scientist at the Institute for Experiential AI here at Northeastern University. And prior to join the Institute in 2023, he worked at Silicon Valley startups focusing on conversational AI. His work included high-level roles as the principal AI research scientist and CTO of Bamboo, where he helped develop this its state-of-the-art digital context semantic engine. In the past, he has held several positions in both private sector and academia, and these positions include positions in American Institute for Research, AT&T Bell Labs, IBM Watson, and Cognos. And he has also spent 7 years teaching computer science at the University of Ottawa, the New Jersey Institute of Technology, the University of Windsor, and the American University of Beirut. And he has published over 45 technical papers, including an award-winning paper that was presented at the German Artificial Intelligence Conference in 2008. So he's going to talk about large language models and ChatGPT, what they are and what they are not. So thank you, Walid, for being here.
Thank you. Thank you for being here, and those also online. Thank you for joining us. Okay, the subject is large language models. Maybe not everyone heard of them, but everyone probably most likely heard of ChatGPT. They're related. ChatGPT is built on top of a large language model. And this is a very long subject. It can take much longer than the time we have, but we'll try to run through the main subjects of interest. First, I'd like to state my opinion on what's happening, because there's a lot of misconception. I call it also misguided hype in the media. So let me quickly tell you where I'm coming from. You've heard probably of things like this coming from even pioneers in AI. We're reading headlines that are really, if we didn't know what's happening, they would be scary, right? AI might lead to extinction. I mean, well, not quite, okay? Don't believe everything you read. In my mind, that's all that happened. What happened is we have enormous computing power. I mean, the computing power is progressing at a scale that's unimaginable. This machine here, my laptop, when I started computing, it would have been considered the most powerful supercomputer on Earth, by far, right? So we have a lot of computing power, clusters of computers on the cloud, amazing hardware speed. We have lots of data thanks to the internet. And guess what? If we have lots of data and lots of computing power to process and crunch this data, of course, we're going to find useful patterns in the data and a lot of insights, right? I call that picking the low-hanging fruits. So we have lots of data, amazing computing power, so we can process it and get some insights from it. Sure, that's useful. But that's all that happened, whether it's image recognition, speech recognition, a lot of useful applications predicting all kinds of diseases, helping in predicting financial outcomes. But we don't have anything we can call human-like understanding. Okay, unless it happened and I was in a coma, but we do not. Okay, definitely we don't have anything reasons like humans. And definitely do not fear any super intelligent AI. So all is well, sleep well, don't worry about anything. So this is where I'm coming from in terms of what you hear in the media, and like as if something is happening and I'm not on planet Earth. So that's my background. Let's see. I'm gonna go now through a brief history of language understanding before I get to large language models. And I'm gonna focus a little bit on the contrast between top-down and bottom-up problem solving in science. The scientific method follows usually either a top-down approach or a bottom-up. And that's going to be important to describe what happened and how did we get to large language models and ChatGPT. So, and then a little bit about the present. We're living in the age of big data. By the way, all these adjectives, big data, large language models, deep learning. So we have big and deep and large. Okay. I'll talk a little bit about large language models and ChatGPT. And I'm going to talk about how we can use these large language models. So I'm going to talk about them going through the good, the bad, and the ugly. But they are very useful. I use them every day in my work, and I'll tell you how to use them very successfully. But then I'll get to the bad. These things are not what we think they are. They are nowhere near what we think they are. And then specifically, I'm going to show you that they do not really understand language. They're very fluent. They can talk forever. They can spit out paragraphs and pages, but they don't really understand what they're saying. I'll show you with examples. And then if that is not it, then what is it? Then I'll discuss some ideas as to how to really get to the language understanding panacea. And then some Q&A. Okay, a brief history. I mean, AI as a computing discipline, the study of cognition and intelligence goes back to before Aristotle, before Socrates even. But as a field, as a computing science field, it really started in the mid-40s, early 50s. Specifically after Alan Turing published his Computing Machinery and Intelligence, and then as a discipline in the early 50s, when John McCarthy coined the term artificial intelligence. But throughout, the discipline was multidisciplinary. In other words, we try to approach these problems, and they are difficult problems. I mean, we're talking about the mind, reasoning, thinking, memories, recall. It's probably one of the last remaining mysteries, the human mind, right? So these are difficult problems. And it was approached in different ways. At times using linguistics as the main foundation, grammar, syntax, languages. At times, information theory and decoding and encoding theory. At times, we incorporated semantics and knowledge structures that were inspired by research in psychology, semantic networks, conceptual graphs, which are the basis of modern-day knowledge graphs, by the way. At times, we did, and then cognition came in, cognitive linguistics. In the early 90s, there was what we call the statistical revolution. Basically, people gave up on the conceptual framework, on coming up with a theory of how language is in our mind and how we think and how we reason. Nobody had a theory. So the empirical revolution came, said, we can't wait for you to come up with a theory. We're going to go and look at the data and analyze the data bottom up and see what we come up with. We can't wait anymore. You make up theories and they don't scale and they don't go anywhere. That was really the genesis of the empirical revolution. Started out with statistical methods, and then neural networks took over. And this is the age we live in. That middle period, although we had many approaches, there were hybrid approaches, but the dominant view was symbolic, linguistic, cognitive science-based approaches, semantic networks, conceptual graphs. And people refer to that period as GoFi, good old-fashioned AI. And now they use it as a bad word. Oh, you're one of those who thinks GoFi is a good approach. Okay, so it's a curse word now. Okay, but throughout, AI kept shifting between these two, the empirical methods, the rationalist methods. And what marks, and they are really different. They are two different, we're trying to achieve the same thing, but in a completely different way. They are really genuinely different methods. And the rationalists follow a top-down approach. They assume a model or a theory, and they work from there to try to explain everything with that theory, or try to see how much their theory explains in terms of actual observations. So it's a top-down approach. Empiricists say, I don't have a theory, I don't have a model, I don't know anything. I'm going to look at the data and see what I can come up with. So it's a purely bottom-up approach. Obviously, the bottom-up is data-driven. I start with my data, my observations. The top-down starts with the theory, right? So Chomsky has the theory, right? Montague has a theory. And they start trying to explain that the whole world fits their theory. That's the top-down approach. In a way, you're playing God. You're saying, that's how I think, that's what I think we have inside our brains, right? You're making a theory. This approach follows deduction. The other one follows induction. The main tool in this approach is logic and reasoning and deduction. The main tool in this approach is statistics and related tools like vector algebra. Okay, the main idea to take from this is top-down requires a theory to start from. You can't start from vacuum. To do top-down scientific reasoning, you have to have a set of generally agreed upon principles or axioms that you can start with. You can't start from nothing, right? And that's the problem. When it came to language, nobody had a clue. What are thoughts inside? How do we externalize our thoughts outside in language? We didn't have a clue, so we were making things up, right? Whether it was the universal grammar, whether it was Montague saying that natural language can be described fully by the tools of first-order logic and lambda calculus and intentional logic. We were making theories and making big claims, saying this is how language is in our mind, without any evidence at all, right? So it is no surprise that these approaches did not go anywhere, while 10 years of bottom-up, let's analyze the data, got us this far. Because at least if I do it bottom-up from the observations, I'll find something. But if I assume a theory and it's wrong, I'll go nowhere. That's really what happened. And the main point I want to make is the success of large language models and ChatGPT has very little to do with neural networks themselves. It has to do with the bottom-up strategy. And this is key because we can do bottom-up symbolically, but that has to wait a little bit. Okay. So in that view, debate between empirical AI and rationalist AI. There's a lot that has been written. By the way, one of us, Ken Church, before I came to the institution, and I know he's here, I read a paper of his that's a very nice review of that history that I went through. And he argues that, okay, there's a reason why we might do empirical, why we might follow empirical methods, but maybe the pendulum has swung too far. Very nice paper, opinion paper, if you want. There's another nice paper in AI magazine about the same subject, sort of a history of what happened throughout language processing, especially between empiricist approaches and rational stuff. And this paper is nice because I've always made the point that NLP is not NLU. Any language processing is NLP. If you take a file and you extract entities, you're doing language processing. Language understanding is a different beast. It's almost a different discipline completely. I even suggested a few years back in a blog, this should be called thought understanding. Because when you're doing language understanding, you're trying to understand the thought behind the linguistic expression. So that's how different they are. And she makes the point here very good. I like this paper. Okay. So how did we get here to large language models, ChatGPT? Well, the symbolic methods suffered from something we call symbol grounding problem. How do our symbols get their meaning? Where does the meaning come from? What is the meaning of a table? In the symbolic approach, we defined it as a predicate and sometimes as a frame or as some node in a graph. The empirical approach was the meaning of a word is we can approximate the meaning of a word from how it's used in language. So similar words are used in similar contexts. If I can replace a word with another word, that means they must have the same semantic underpinning or conceptual. Like if I say, I had X for breakfast, then all the things that can be the value of X must be similar because I'm using them in the same context, right? The distributional semantics hypothesis is a little bit more involved, but essentially similarity in meaning is similarity in contextual use in language. And we had the idea of modeling the meaning as a vector, which is a point in multidimensional space. Here I have 2 dimensions only, but think of it as, here I'm defining the meaning in terms of only 2 dimensions, age and gender. Think of them as 2 features or 2 attributes. But you can imagine many others, right? Actually, in practice, our vectors are 300 dimensions, 500. The latest in GPT-4 is over 1,000 dimensions. But let's define only across 2 dimensions. So man and grandfather are similar when it comes to gender. Child and infant are similar when it comes to the age feature or the age dimension. Now, if you can imagine another 10 dimensions, let alone 200, you can imagine how many really granular aspects of meaning we can cover in a vector. That simple idea. Oh, by the way, the brilliance of this idea is that now meaning is a mathematical object that computers understand. So now I can compute with meanings. Before that, they were just characters, right? Now I have a mathematical object that I can compute with, so I can add and subtract. This is a famous equation that they usually use. If I take the vector of king and take from it the gender and add to it another gender, then it becomes close to queen. And actually, if you try that, it works. If you have a tool where you have embeddings and has vectors, and you try this, it works. The similarity with these two becomes very close. So it's a neat way to represent meanings and compute with them. And that was the genesis of everything we are hearing about today. We had word embeddings like these. The first were things like word correct, love. We improved on them by extending the context, and so that we are embedding not just features, but larger linguistic dependencies. If you want structural dependencies like grammar, really. And then came transformers, which are the basis of GPT. Transformers added not only wider context, so that we are encoding, if you want, almost the grammar of language, but it added a positional encoding. In other words, the position where the word, not just the context, but the absolute position of the word matters, right? This is important for reference resolution, for scope resolution. So with that, they managed to encode the proper way of speaking, the syntactic structure. That was a big innovation. That paper came out of the Google lab. Okay, so like I said, we encode the position, not just the wider context. There are many papers that describe it's quite involved actually, but there are many sources where you can take a high-level view of how this thing, or the idea behind it. And basically, that allowed us to build a predictive engine. You give me a piece of text, I can always predict the most plausible word that should follow. Imagine, all that ChatGPT does is predict the next word if you give it the prompt. But if I can keep doing that recursively, I can keep predicting the next. I'm generating text. That's the simple idea. Now, the next word that is predicted is not always the one with the highest probability. We put a threshold, and between those, we pick a random one, so that to simulate creativity and not always repeat yourself. A nice trick, but the same idea. Okay, to get here, what did it take? Actually, the numbers here are old. We are now above 5 trillion. But even if we stuck to around trillion, that's about 10 million books. That's how much GPT-4 read. That's like 20,000 people living until 80, all of them would read. That's a lot of language. So if that's how we learn language, we would have to wait a child until they are 160,000 years old for them to speak, like GPT. Obviously, that's not how we learn language, right? But we got a tool that did the job. The point now is scale, we know now, doesn't matter anymore. There was a point where the more parameters we put in the network, the more language and text we ingest, there was improvement. It got to a point where more doesn't improve anymore. We plateaued, right? Which statistically makes sense. You get to a point where everything you need to discover from the data you did discover, you picked up all the low-hanging fruits. The rest are way at the top. You can't get to them. Which means, but we'll get to it later, which means what's next? Should we stop AI and say ChatGPT is the best we can do? Okay, again, there's a nice review on large language models and how they work, how we got to them. This is a bit more technical, but for the technically inclined, it's a good review paper. And if you like to use them, it's so easy to use them. You install transformers, and then you can import any model, the BERT model, the Llama model from Facebook. And pipeline is important because pipeline is what you instantiate. So the task, let's say I want to do summarization. All I do is I instantiate the pipeline with the task summarization, and I choose the model I want to use. I want to do question answering, and I want to do it with this model. That's it. This is all you need. And you can do some amazing stuff. This one I'm going to get to later on. This is a nice function. Remember, these models, because they read everything that they can read, they can predict what is the most likely word that can come here. They can do fill in the blank very well, right? So that can be used to do amazing stuff. I'll show you later. But for now, I told it, give me the mask values for these. And I asked for only 3. I can ask for 20. And it comes back ranked and with a score. It told me the most possible way of describing book or humanity from everything I read describes book usually by saying mostly famous. This is a very famous book. This is a very popular book. Keep that in mind. That's powerful stuff. I'll give you a hint. I can reverse engineer how we talk doing something like this. I can go and query, how do people generally talk about books? I'll tell you why that's useful later, okay? But keep that in mind. Okay, so like I said, there are all these tasks: question answering, sentiment analysis, fill in the blanks, you name it, there's a lot. And all you have to do is install, import, and instantiate the pipeline. You find the stuff mostly on Hugging Face, some on Kaggle, some on GitHub. Okay, another way we use this thing, other than just the window of ChatGPT where I can toy with it and ask a question and get impressed, wow, how does it know that? Is in applications, we can use it to do question answer. But to do that properly, because these large language models don't have factual information about specific field, like in your domain as a country. They have general knowledge about text they read. What we do to use them properly, you've probably heard of prompt engineering. You give it a prompt that is specific to your situation. Well, that works, but it still doesn't guarantee that it will give you the right answer. Or you can fine tune it, we say, basically, or retrain it from scratch. These are almost similar, but fine tuning doesn't have to do the whole thing. And the idea here is you give it content that's related to your domain and retrain it with your own content, and that's fine tuning. But the most powerful approach is this. And this picture explains what's happening. You index your domain knowledge, your company's documents, right? And before you ask a question, you go and retrieve content that's relevant to your question and use that as a context in your prompt. So basically, you're telling the LLM, you're spoon feeding it, basically. You're telling it, I'm going to ask you a question, but don't go wild on me. Use my content to go and look for the answer. And then it does a very good job. I use it now to do many things, actually. Okay, so this is all the good. We have an amazing technology. We know how we got here. But it is a lot less than what people are making it to be. So now I'm going to take out the guns. But I'm not the only one that has spoken of the limitations. maybe I have from the beginning, but people are starting to realize now that we're employing this in the wild, in reality, we're starting to discover all the limitations that some of us talked about, and I'll mention some of them. Even one of the pioneers of deep learning is saying, I mean, he's using words, that's a bad word, right? That's like a scammer. Or like he's saying, there's a lot of lying going on. Stop spreading the news. So people, but I care more about the research community. So let me go through some of them. Oh, yeah, and you have people on the other extreme saying all of this is nothing, which is also not true. Something huge happened and it's useful. So usually the right answer is in the middle, not exactly in the middle, but in between. But we're starting to realize that there's something else, right? This is not the end of history. This is not it. We need to incorporate reasoning and symbolic approaches. And even DeepMind is starting now. That's very recent. They published a paper, and I heard one of the leading scientists on this. They're starting to employ symbolic approaches, in this case, category theory, but essentially it's logic and type theory to build deductive engines, because purely discovering patterns in data statistically is not going to get us there. So now let me go through some serious theoretical issues with large language models. People like to cite that, but a lot of research is being done on them. First, before I go through these, the phrase large language models is misleading. These are not language models. These are models of linguistic statistical regularities in language. Language models would tell me something about language. If you go and peek inside a large language model, this black box, the deep neural network, you don't see anything about language. You don't see syntax, you don't see semantics, you don't see concepts, you don't see meaning, you don't see anything. You see weights, numbers. There's no language model here. So LLM is a bit misleading. So basically, if you open an LLM and look inside, what you see is the same thing you would see if you opened an image recognition network. Weights. There's no language, anything inside, right? So they are not language models, they are models of statistical regularities in language. Another thing that we discovered is that, which is a bit technical, but I'll summarize it in a couple of words. Neural networks, the vectors that we talked about, the only operation you can do on vectors, does anyone know what is the only thing I can do with two vectors? Similarity. Like I have 2 points in space, the only thing I can measure is the distance between them. And the less the distance, the more similarity they are. That's the theory, right? So the only thing I can do with two meanings in these approaches is measure similarity. There is research and there's proof in this paper that similarity is not enough. We need identity. Similarity lets us go into what is called an infinite regress. This is similar to this, and this is similar to this, but that doesn't mean this is similar to this. So you get to a point where you miss out the real identification of an object. It's a technical result, but it's a serious problem to this approach. A more serious approach, well, they're all serious, is a result that came out of Stanford University, and it's called model collapse. I'll explain briefly what it is, but it's a book. These LLMs need lots of data. And at some point, the content they're generating is being ingested by them in the training data. So what will happen, and they proved it technically, theoretically, what will happen is these large language models will get fixated on some probabilities in the network because it's being reinforced by their own previous predictions. Basically, they get to a point where they're believing their own lie. Think of it this way, I mean, metaphorically, right? But if they start training on their own data, They're not discovering patterns anymore. They're reinforcing the predictions they made before. And so the network settles on a place and starts not going anywhere else. It's called model collapse. Very important result. Other issues, truthfulness, ground truth. LLMs have no access to the ground truth. For an LLM, all text was created equal. They don't know that this is true, this is not true. It's all text, right? There's no notion of facts and ground truth. Another big problem is these models need a lot of data. And so they're under the mercy of the data they ingest. So if the data has bias and toxicity and offensive language, it will get incorporated in the network. And we will always have that. Another term that I don't like, but they somehow it somehow became the common word for this phenomenon, hallucination. I don't like it because to hallucinate, you have to be intelligent, actually. The most intelligent people hallucinate. Van Gogh hallucinates. The point is, they're not that smart to even hallucinate, but we call it hallucination. And essentially, it's when the predictions and the statistics go off, which can happen anytime in statistics. We call it hallucination. Basically, when the predictions become off topic. And the important thing here is that all of these, everything I mentioned so far, is not something we can fix if we want to stick to deep neural networks. These are all issues that are a function of the paradigm itself. So these are quote unquote in theory issues. They are not issues that can be fixed with more data or if I change the topology of the network. No, all of the stuff is hand waving. Another big issue, which I wrote about, is explainability. Neural networks, deep or shallow or any neural network, cannot explain its output. Explainability is inference in reverse. Basically, you come and give me a prediction, an output. I say, explain yourself. You do deduction in reverse. You explain to me how you got it. That's explainability. In neural networks, whether I have 1 neuron or 2 trillion, doesn't matter. This is the computing element. And then we have 1 billion of those connect. That's fine. The computation happens this way. I have inputs, I have weights, I do a weighted sum, W1 times X1 plus W2 times, right? And the output of that goes to an activation function, usually the loop, and then you get an output. It doesn't matter, but in the end, you have a value that was computed from the inputs and the weights. If I ask you, how did you get 12? Explain yourself. You can't in a neural network. Was 12 this or this? How many ways I can get 12? Infinite. You want me to try? I can get 12 in an infinite number of ways using addition and multiplication. Okay? The point here is whether this is a vector, tensor, or a scalar value, decomposing this into its original component cannot be done in a neural network. End of story. There's a lot of people that I don't know why they have a hard time understanding this concept. So it's not a concept, actually. It's in symbolic computation, I can explain myself because I keep a semantic map of the computation in structured objects like an abstract syntax tree or a graph. So I can always go back and explain how I got to 12. A few days ago, actually, I tried to explain that. I said, okay, you didn't like it from a function composition point of view. Maybe with picture, you will be convinced. In symbolic approaches, I have objects like this, structured objects. The neural network is these objects all crushed into millions of neurons like this, right? Now, on the left-hand side, I can explain how this can stay holding up. I can say, you can remove block S10, you can remove S1, but you cannot remove S6. I can reason and explain how this is holding up, and if it fell, why, using my structured objects. Can you here explain to me how this will hold? And you have to use the blocks. You have to refer to the original input. Where are the blocks here? The point is, in a neural network, the components of the computation are gone, they're lost. So explainability is hopeless, regardless of all the hand waving. Okay. I tested these on planning. I read a paper, references here. And when it comes to planning, which is a big thing in AI, without planning, we will never have AI. To build a robot that we ask it to go and make me a coffee, they have to make a plan. Planning is a big thing. It's not all about language. We tested them on planning. Less than 1/3 of the time, they came up with a plan that makes sense. And this is a plan that a 4-year-old can do. If you get this to a 4-year-old and you say, can you take me from here to here? Yes, they might take a long time. Maybe we can do it faster, but they'll take us from here to here. A 4-year-old, they'll take this, right? And you can test ChatGPT on this very easily. You give it the rules. I tested it 10 times. It actually performed less than 1/3. Give it a small plan like this. Say, please show me the plan of going from here to here. So it's less than random, the success rate. And those that know how these things work, I'm not surprised. Because to do a plan like this, you have to save in memory the state of affairs, and the state is a structured object. Neural nets don't have any of that. Another paper that showed that if you do analogical reasoning, something also for children can do very well. You give it a sequence like this, and you say the output should be like this. Basically, you're telling it, write the next one. Then you give it another one and you say, what's the output? Oh, you saw the pattern, right? It's called analogical reasoning. But these guys were smart. They gave it an alphabet that's not the usual alphabet we have. Well, it is the usual alphabet, but not in the order we are used to, because they didn't want the network to rely on what it has memorized. And again, GPT 3.5, little bit more than third success. The state of the art, not even half the time, it got it right. Okay, so as a reasoning engine, forget it. How about language? Their claim to fame is language. Do they really understand language? So, but when I test it, I don't test it like I'm writing a story about a Superman that has these powers, blah, blah. If you give it that from everything it read, it can write a book. It will never stop. That's not really language understanding. Language understanding is about testing the real inferencing that is going on. Did it really fully understand what I'm saying? I'm not asking you to show me your creative power in generating text. So here's a real test for language. I'm going to write a paper about all the tests I'm doing. I said, suppose that Sarah read a story on her way home about a labor revolt in Paris. Just a prompt. And then I said, which of these is more plausible? Sarah went home driving her car. Sarah went home by train. Sarah went home walking. How many would choose? What do you guys choose? Two. Two? Anyone will choose something else? I said, which is more plausible? I didn't say which is the one. Which is more plausible? A 4-year-old will say by train. I don't see people driving and reading. I mean, maybe there's a loony or two out there, but usually 2 is more plausible. For ChatGPT, because they all can happen, they're all as possible. This is called abductive reasoning, very powerful technique. It's reasoning to the best explanation. What is more plausible, right? It's also called plausible reasoning. So they always fail. I'm showing one test, but here's another one that is interesting because it tests a deep problem in AI related to the frame problem, the famous frame problem in AI. Long story short, forget that. I said, my 4-year-old came with her classmate. Classmate here, I said, so that the friend is also roughly 4. Wait, 4 give and take, right? But not 10, right? 4 or 5 or a little bit. And I said, her friend told me that she's going to be applying for a senior scientist position at the institute I work at. And then to take the ChatGPT somewhere in the chain of thought, I said, is it moral or ethical to put in a word for her just because she's my daughter's friend? It concentrated on the ethical issue and it forgot completely that I'm talking about a 4-year-old applying for a senior research scientist position. No common sense at all. Okay, other deep linguistic understanding phenomena. I said I threw away the newspaper I was reading when I knew it fired the columnist that I like, my favorite columnist. Here I'm using something we call in language or in cognitive science co-predication, meaning I'm using one object to refer to it in different types. The physical object, the content, the company, right? So I threw away the physical paper, but obviously the physical paper is not the one that fired the columns, right? And then I say, basically, show me what you understood. Show me the entities that are involved in this content. Newspaper for it was physical object. To make sure I'm giving it another chance, I said, draw me the graph. The newspaper, the physical object, is the one that fired the columns. Now, I've never seen an actual newspaper fire a columnist. My point here is that there's no deep understanding of what's happening inside. Right? Of course, I'm not fair in testing it, but my point is to find the issues, not to be impressed. Okay, this is co-predication, but at a larger scale. I said the city of Barcelona celebrated on Sunday after it won over Real Madrid, Barcelona, as it was getting ready to vote for independence. Here I'm using Barcelona to mean at least 3 things. The city, explicitly I'm talking about the city. It won over Real Madrid, not the city, the geographic location. Barcelona, the football team, won over Real Madrid. And the football, neither the football team nor the city are going to vote. It's the citizens of Barcelona. So I'm using Barcelona to refer to 3 things at the same time. Well, I said the city of Barcelona, and that's the only entity it found out. Where's the football team? Disappeared. Again, to make sure, give it another chance. Show me the graph. Okay. If you go to things like prepositional phrase attachments, Sarah read a story about evolution in the last 10 minutes. If I take the last 10 minutes and I say, Sarah read a story about evolution in the last 10 million years. Now, 10 million years is for evolution. But in the last 10 minutes is the reading period. No clue. Why? LLMs do not know that it doesn't make sense to speak of evolution in a 10-minute period. And it doesn't make sense, even worse, to speak of a reading event that took 10 million years. Okay? Enough, have mercy on it. Intention is a logical concept that logicians have worked on for Okay, many problems. You can go through them later. Now, I want to spend a minute or two. These LLMs have done, like I said in the first part, amazing job. We got powerful stuff. But what worked is that the reason we got here is not because of neural networks. It's because of the bottom-up reverse engineering smart strategy. Let's see what the data tells us. If we do that in a symbolic, semantic, cognitive way, then we get the best of both worlds. We discover what language is all about, but symbolically and not statistically and widely at some time and without any reference to knowledge and common sense. This can be done. I'm working a lot on this. We can actually use LLMs themselves to fix them. So we can discover all this stuff by querying large language models and build things like this. Build vectors, but not statistical vectors, symbolic vectors. This says the most likely thing we do with cars is driving them, buying them, repairing them, blah, blah. We can discover all this stuff. How we talk about things in language tells us, these are the slides I skipped. To know what's out there and what are the concepts and meanings in our head, let's discover how we talk about them. So if we do that in a symbolic setting, we can do powerful LLMs that can reason and don't do the funny stuff I was going through. Sorry, I had to skip a few slides, but we can do some questions and answers now. I never finish on time. I didn't know why.
Thank you, Walid, for the talk. That was really insightful. And I think one thing I like is that you clearly explain all of the limitations, but you still acknowledge they're useful, right? The current.
I use them every day at work.
That's really nice.
My whole point is that that's not the end of history. There's still a lot more to do.
Nice. Okay, so do we have any questions here in the in-person audience? No questions here.
Yes.
Oh, there's one question there, so just give me 1 second, I'm gonna give you the mic.
So you said LLMs have captured the low-hanging fruits, and there's still top-hanging fruits left to be captured. Is that the logical reasoning and everything which are top-hanging fruits?
No, I meant here.
Yeah.
That's a good question. I meant they are good to pick up the obvious stuff, right? But there's the examples I was going through, they're very deep, they're not easy. Like the newspaper, I threw the newspaper because it fired my favorite columnist. I'm using it as a physical object, and these are not, okay, for humans, they're easy, but for LLMs, these are not low-hanging fruits. They cannot find this in patterns of data, this deep knowledge. And I've written about this, that most of the deep knowledge that we use in language understanding is not written in text. So you're not going to find it in the data. You're trying to find something that's not there. So that's what I meant by the higher fruit. There's stuff that's not so easy to pick up just by finding patterns in the data. It's deeper than the linguistic structure.
Basically, it is not empirically.
Exactly. It's related to rational thinking. And one example I showed has to do with abductive reasoning. It's not about the data itself. So data-driven empirical methods won't help. You're looking for something that's not even there.
Should we do an online question?
Okay, if I understood you, there are LLMs existing or in development that are beyond general and are more field specific. Are there medical LLMs, and how developed are they?
Yeah, good point. There are medical LLMs, there are financial LLMs, there are domain-specific LLMs. I went through briefly that you can do fine-tuning So yes, we can train these LLMs on our domain knowledge, our corpus. It could be medical, life sciences. There are many LLMs that have been fine-tuned for mostly in the medical and life sciences, yes. But there are others in the financial sector, in the legal sector now. Basically, you retrain the model with your own domain corpus.
Thank you. You showed that explainability is impossible in LLMs, yet there are companies receiving hundreds of millions that claim they can do it. What are we missing?
What we're missing is wait a couple of years and go and check where these companies are. No, I don't want to be that cynical, but yes, the people have underestimated the explainability problem. There are companies that are claiming they do explainability now. What they do is they explain, the middle is a black box. There's no explanation. They give you a dashboard and they say, if your inputs have changed slightly like this, they plot so many charts showing you accuracy and output, how it would be. But that's not explainability. They cannot tell you exactly why they reached this decision. They show you input-output functions and how the input was mapped to the output. But the honest answer I have, they will not go anywhere. That's a prediction. Sometimes I like to make predictions.
Does anybody in the room have another question?
Yes.
Yeah, I can just ask you. Thank you. This is just building on your question, and you talked about like the top down and the bottoms up approach, like it's more of a dichotomous approach, like you just like had two categories. But you also mentioned about the LLMs being more bottoms up, they're just analyzing data and stuff. And maybe that's the reason they're lacking the explainability, like common sense and all the limitations that you mentioned. What are your thoughts on having some sort of like the third category where you have something like top down? You give them the context, which could be a theory or like a scenario where they can build. I mean, like that's also going to be something on like statistical, like probabilities of what things might happen and might not happen. But how about like in the future, there's scope for like mixing top down and bottom up depending on the situation of the scenario?
Okay, that requires about another 40 minutes, but briefly summarize. There are approaches where people, they call it hybrid AI, they call it neurosymbolic AI, right? I don't think this will work, and this is not a new idea. We tried this in the 80s and 90s. What I believe will happen, there's a room for this bottom-up pattern recognition paradigm. I'm not diminishing it. That's how we do, for example, image recognition. We recognize patterns, and now I know what a flower looks like. It's ideal for this paradigm. Every paradigm has its place. So I'm not into this hybrid. I'm into what Marvin Minsky called modular AI, the society of mind, or Jerry Ford calls it the modular mind. In other words, I have a module that is good at pattern recognition. That's it. And it probably is a neural network. Bottom up, it discovers a pattern, and now it knows how to recognize patterns. I probably have a module that does statistical reasoning, one module that does logical reasoning, one module that's good in counting and arithmetic. And the mind is a huge system of modules working together. So hybrid neurosymbolic is a cop-out. It's like, this is good, let's put them together. This is not science. But modularity, yes, we have modules that are specialized in one thing. We have a color module that's good in interpreting colors. That's it. But we don't try to make it do everything else. So the mind is modular in my mind. It's not hybrid. The whole system in the end is hybrid because it has statistical reasoning, logical reasoning, pattern recognition, language analysis. Did I answer?
Yeah.
And I didn't need 20 minutes.
Okay, so unfortunately, we don't have time for more questions, but there's going to be a follow-up blog post during the next days answering more questions that we didn't have time for. Please let me remind you that next seminar is in 2 weeks, and we will have Ron Bradman, who is a visiting professor at Cornell University, and the title of the talk will be Giving AI Some Common Sense. So thank you everyone for participating today. Thank you, Walid, for your talk, and see you next time.